Okay, dear students, in previous sessions we have discussed a lot about the ambiguity. We have discussed about the ambiguity of words in the language and thereby ambiguity in grammars. Okay, then we have discussed ambiguous and unambiguous context-free languages, and we have discussed about the inherent ambiguity. So we have discussed a lot about the ambiguity. And we have also concluded that if language represented by a particular grammar is not ambiguous, then if the grammar is ambiguous, we can convert this to an unambiguous grammar. Today, we will discuss how we can convert this ambiguous grammar into the unambiguous grammar. So, we will discuss the removal of ambiguity. It simply means we are having an ambiguous grammar and the corresponding language is not ambiguous. So, we will try to convert this ambiguous grammar into the unambiguous grammar. If the language represented by the ambiguous grammar is also ambiguous, then it is not possible to find an unambiguous grammar corresponding to that. When we convert our ambiguous grammar to unambiguous grammar, there is no general method, there is no fixed algorithm for it. Okay, so we have to find some strategy which may be successful. In some cases it will be successful, in some cases it may not. Okay, so the strategy is we will try to identify the reason of that ambiguity. From what reason the grammar has become ambiguous. We'll try to find that reason and then try to remove that reason. First we'll identify the reason and then we will try to remove it. So possibly we may find an unambiguous grammar from an ambiguous grammar. Now we'll first discuss what may be the most common reasons which makes a grammar ambiguous. So the most common reason, most common causes which makes a grammar ambiguous are number one, common prefixes or suffixes. And the second reason is presence of left and right recursion both simultaneously. So we are having both left and right recursion present in our productions, or we are having, or our productions are having common prefixes and suffixes. So these are the most common reasons. We will discuss these in detail. Okay, and moreover, this is not these two are not only the reasons. There may be many other reasons also. So you have to identify from the grammar what is the reason and how it can be corrected. We will be discussing these most common two reasons in detail. Now come on the first reason, that is common suffix. In this common suffix, we mean that suppose there are two productions of this form S to A, B and AAB. So if we look at the leftmost symbol, this B, this portion and this portion, this is common, and portion before it is different. So this is called a common suffix. So these two productions of same variable are having common suffix, that is B. Okay, so this is called common suffix. Similarly, if we come on the common prefix, if we look at these two productions, these are productions of the same variable, suppose X. So initial part is A. So this is also A, this is also A. So this is a common prefix. Portion after this common prefix may be different, but this common prefix is common. And it is not necessary that there will be only a single variable here. There may be multiple variables. Suppose AB is here. Suppose my production is of the form, suppose ABC. And this is suppose AB and AB. Okay. So in that case, this AB, this portion is the common prefix, because in initial part of these two symbols is same in both the productions. So this is called the common prefix. So these are common suffix and common prefix. We'll look at how these will contribute to the ambiguity and how we can remove this. Okay. Now come on the next problem. That is the left recursion. Left, what we mean by left recursion? Left recursion, we mean that leftmost symbol on right side of the production is same variable as on the left hand side. Okay, one example may be taken like this, X to XAB. So the leftmost symbol on the right side, this is the right side of the production, we have to take its leftmost symbol. So this leftmost symbol should be the same variable which is on the left side. So if same variable which is on the left side occurs as the first symbol of the production, then we call that this is a situation of left recursion. Why we are calling it as left recursion? Suppose we derive something from this production. So we will start from x. X will derive x a b. So it will derive x a and b. Okay. Then a and b, these two are something else. Now we have to expand this x. So whenever we expand x, again we will use this. So it will be x a b. So if you look at our derivation tree is growing towards the left side. So that's why it is called left recursion. So I hope now you have understood what we mean by left recursion. In the similar manner, we can define the right recursion. Right recursion is nothing but the rightmost symbol on the right side is same variable on the left side. So rightmost symbol on the right side. So right side of the production is this. Okay. And the rightmost symbol. Now this time we are not taking here we have taken the leftmost symbol. Now we are taking the rightmost symbol. So rightmost symbol on the right side should be the same variable on the left side. So if the variable which occurs on the left side of the production is occurring as the rightmost symbol or the last symbol of the production, then we call this is a right recursion. Okay, we can just find its derivation. From x we will derive ax, then again we will expand this x, we will derive ax, again we will expand this x, we will derive ax. So we are looking at our tree is growing in right direction. So that's why we call this as the right recursion. So this is left recursion, this is right recursion. We have discussed common suffix, means the end portion of the productions are similar. Common prefix means the start portion of the productions is similar. So these are most common problems which we will be discussing in our examples. Now we will start taking the examples in which we will consider these problems and see how we can remove these problems. Now come on, our first example. The grammar is S2 capital A capital B, and second production of S is A capital B. The productions of A are these: A capital A oblique A, and the production of B is B to simply small b. Okay, so this grammar we have also seen in previous discussion of ambiguity. We know that this is an ambiguous grammar. Okay, and what is the reason that this grammar is ambiguous? If we look at the productions of S, we can see that we are having B as suffix. So common suffix problem we are having here. Now we'll look at how this common suffix problem contribute to the ambiguity. We will analyze this grammar. Suppose we have to derive some word from S. So we will start from S. Suppose we are taking the production S to AB. Okay. Then from A, what we can generate? We can, if you look at these productions of A, we can generate more than one A's. So at least one A we have to derive, or any more number of A's if we wish we can derive. So one or more A's can be derived through this A. What can be derived from B? From B we can derive only a single B. So obviously the language is L is equal to A asterisk B, or we can say A asterisk AB. So the minimal word in this language will be AB. So words in this language will be having the format AB or double AB or triple AB or four ABs and so on. Okay. So like this will be the words in this particular language which will be generated from this production S to AB. Now what can be generated through the other production of S, that is S2 small a capital B. Okay, so small a, these two are terminals, so these will be fixed. And what we can generate from B? From capital B we can generate only the terminal letter B. So what word what word is contributed by this particular production? That is only a single word, that is AAB. So this word. So it will not have any effect on the language. Okay, because this word is already being generated through this. Okay, and now because this word AAB can be generated through this production as well as through this production. Okay, because of the common suffix problem. From B we can generate only a single B, and in this we are having double A, which can also be generated on the left hand side of the variables available on this production, that is capital A. From this capital A we can also generate double A. We can use capital A to AA, so one A will be there, and then we can replace the A, capital A, by small a. So in this manner we can generate double A also from this capital A. So that's why the word AAB can be generated through this production as well as through this production, and thereby we will be getting two different derivation trees. Okay, and we have seen that this production is contributing only this particular word, nothing else, nothing else. So if we remove this particular production, if we remove this particular production, then we do not have any effect on the language generated by this particular grammar. But if we remove this production, among the two derivation trees which are available for this word AAB, one derivation tree will be removed. So only a single derivation tree will remain for this word AAB. So thus the ambiguity will be removed, because there is in this whole language there is only one word AAB for which we are having two derivation trees. Otherwise, all other words will be having only a single derivation tree, because they are being derived through this production only. They cannot be derived from any other production. Okay, so just removing this production will solve our problem. So normally in case of common suffix or common prefix problems, we will identify those productions which are having common suffix and prefix and which are not having any impact on the language. Means the word which are being generated by those particular production is also being generated by the other production. So we will remove such production. So just by removing this production will give us the modified grammar. So now this is the modified grammar, and you can see that this is unambiguous. Okay. So this is how we can handle the common suffix problem. Now come to second example, which is having a common prefix. Just look here, which is having a common prefix. So A is here, and the next portion it is the variable B, and here we are having a small ab. So it is having the problem of common prefix. We will examine this language. First of all, we will look at what we can derive from S through this particular production, capital A, small ab. So through this we can generate S to AAB, and what we can generate from this A? From this A we can generate only double A, small double A. Okay, what we can generate through this capital A, AB, it is a word double A. From A will be derived double A, and then we are having AB. So this word we will be able to derive. What we will be able to derive through this? Obviously, in this from A we will be able to derive double A. Okay, and what we can derive from B? From B we can derive A plus B asterisk. You just look at our productions are B to small a capital B, small b capital B. So if we wish a small a, then we can use small a capital B this production. If we need a small b, then we can use this production B to small b capital B. Okay, and when we wish to remove this variable capital B, we will remove it through the epsilon. Okay, so the language is double A plus B asterisk, means all words which starts with an double A. So this will be the language. Okay, so all such words can be generated through S to AB, A to double A, B to AB, BB, and epsilon. Okay, now what is being generated through this? The only word double A, AB will be generated through this. So in this whole language, only this is the word which is having two different derivations. So it will be a ambiguous word. This word we can generate from this production S to AB as well. From A, double A we will be generating, and from B we will be generating small a. How? First we will use B to small a capital B, so small a will be there. Then we will be using for B capital B to small b capital B, so B will be generated. So after double A, AB will be generated, and then we will remove B by epsilon. Okay, so in this manner we can generate this particular word. Okay, and this word is also being generated through this from S to capital A, AB. So a small AB is already there. Okay, from A we will derive double A. So in this manner also we can derive this word. So this word is having two different derivations. So it is an ambiguous word, and the grammar is ambiguous. And we have seen that the problem here is the common prefix. And how we can remove get rid of this problem? By removing the production which is producing the additional which is producing the word which is also being produced by the general equation. So from this we are able to generate all words in this language. So this is only producing a single word. which is also included here. So what we will do, we will just remove this production, and our grammar will be, the remaining grammar will be the unambiguous modified grammar. So we will remove this, and this will be the unambiguous modified grammar. S to capital A, capital B, A to double A, and B to this. So this is how we handle the common prefixes and common suffixes. Now come on the third example. Our grammar is E to E plus E oblique A. So this grammar is used to generate a arithmetic expression involving only the plus operation. Okay, and E is our start symbol in this particular case. If we carefully look at the productions, we look here that in this production we are having the presence of both left recursion and right recursion. Why it is left recursion? Because in this production the leftmost symbol is the same variable which is on the left hand side. So that's why it is having left recursion. Why it is having right recursion? The rightmost symbol in this production, is the same variable which is present on the left hand side. So that's why it is having the right recursion. So in a single production, we are having both left and right recursion simultaneously. So as per our discussion, this should be a ambiguous grammar. But let us prove that this is an ambiguous grammar. For this, we will take a word W, which is of the form A plus A plus A. So suppose for this expression, we want to derive this particular word from this grammar. Okay, so let us see how we can derive it. We'll start from E, and because we want pluses, so we are bound to take this E plus E. So we are taking this E plus E. Now on the available variables, we will expand the leftmost variable. So this E we are going to expand. So again, suppose we use E plus E, because we want 2 plus 1 plus we have already generated. So one more plus we have to generate. So we will generate it from this E plus E. Again, now among the all available variables for expansion, we will expand the leftmost E. So the 2 plus we were requiring, and we have generated these 2 plus here. So now from this E we will convert it to A using the production E to A, and similar we will be doing here E to A, and then similar we will be doing here E to A. So this is one derivation for this particular word, A plus A plus A. Now what may be the second derivation? Again we will start from E. We will use E plus E. Okay. Among the available variables, we will expand the leftmost, and this time, last time we have expanded it through E plus E. This time we are not expanding it through E plus E, we are expanding it to E to A. So we are expanding it E to A. Now we'll come on the next variable. We will expand it because we need one more plus. So here we are bound to use E plus E. So we will use E plus E here. E plus E here. Now again, among the available variables, the leftmost will be expanded, and because 2 plus we have already generated, so we'll use E to A and we'll convert it like this. So E to. Now these are two derivation trees we are having. So for a single word, we are having two derivation trees. So in this manner also we have proved that the given grammar is ambiguous, because this word is ambiguous, so the given grammar is ambiguous. Now we have to remove ambiguity from this grammar. So here the reason of ambiguity was presence of both left and right recursion simultaneously in a single production. We can get rid of this problem either by removing the left recursion or the right recursion. So among both the recursions, we have to remove one kind of recursion. Okay. So now question is, which recursion we will keep, which recursion we will remove. So this answer will be given to us from the question, which among the available these two derivation trees, which one is correct, which one we want to keep. If we go by the arithmetic expressions, our plus operation is left associative. Means if expression is A plus A plus A, so first this plus will be evaluated. So basically this expression is something like a plus a. So first this will be this operation will be performed, and with the result of this operation, this plus operation will be performed. Okay. So which of these two trees reflect this operation? Obviously this one. So this is the correct one, and this is the wrong one. How this is reflecting this? If we look at, for performing this plus, we need the answer of this expression. And to get the answer of this expression, we need to perform this plus. So first of all, this a plus a will be performed. Its result will come here. Then in this result, this a will be added. So which is the functionality which we need in this particular expression if our plus operation is left associative? Similarly, our plus operation is right associative, then this one will be correct and this one will be wrong. So for right associativity, we will be needing the structure of the derivation tree like this. And for left associativity, we will be needing the structure like this. So in this manner, we have decided that this one is the correct structure which we want. So our operation is left associative. If our operation is left associative, then we should keep the left recursion and we should remove the right recursion. If our operation is right associative, then we have to keep the right recursion and remove the left one. This is a simple key to find the modified grammar corresponding to it. Now here from this we have understood that we have to keep the left recursion and we have to remove the right recursion. So what we will do, we will keep the left recursion. So the modified grammar will be e to e plus, because this e we have kept as it is because we want to keep the left recursion, but we don't want to keep the right recursion. So here we will not put e. What we will put there? What can replace e? What other things can replace e? We will replace it by that. Okay. So e can replace a, so we'll replace it by a. And other productions will be similar. Now this is the modified grammar. And you can see that this is unambiguous. If you go by this grammar, you will be able to generate only this kind of a structure. Just look at. We are again trying to derive this word. So we will start from e. We have to use, we want pluses. So we are bound to use this e plus a. Now you look at here, we are having a on this side. So this is the only variable which we can expand. So we are bound to expand this one, and the one plus we have, another plus we want. So we are again bound to use e plus a. So we will be using e plus a. And then we will expand this e. We will expand this e by a. So first, how the operation will be performed? First, this a will be evaluated. Its answer will come here. Then these two a's will be added and answer will come here. Then with this answer, this a will be added and we will find the final answer. So means first these two a's will be added and then in the result of this, this last third a will be added. So it is a structure of this kind which we want. And other than this, we cannot generate any other structure. We are bound to use this. Okay, so we will not be able to generate this structure. Why we were able to generate this structure? Because of the presence of this right recursive e, which is not present here. So on the right hand side, we cannot we cannot expand. Okay, so we will be expanding only in the left direction. So this kind of a structure we will be getting, and we will be getting an unambiguous grammar. So this is also known as the associativity problem. So if left problem is left associative, we will keep the left recursion. If the problem is right associative, we will keep the right recursion. Now come on the next example, that is the fourth example. This fourth example is e derives e to the power e oblique a. So here this symbol represents the power symbol. Okay, so a raised to the power b. Suppose I write a, this arrow b, so it simply means a raised to the power b. It is also a arithmetic expression, and if we take a word of this form a to the power a, and we will try to derive this word from this grammar, we can find the two derivation trees as we have done in the previous. So you just look at, we'll start from e to e, arrow e, and then suppose we are expanding this E again using E arrow E, and then E to A, E to A, and then E to A. And this one we are getting E to E arrow E, and then first E we are replacing by small a, and then second E we are replacing by E to the power E, and then E by A, and then E by A. So again we can find two different derivation trees for this particular word W. So this word is ambiguous and the grammar is also ambiguous. Now again question is, among these two which one is correct? As the power function, this power operation is right associative. Just look at, if we are having an expression 2 to the power 3 to the power 2, what will be its value? Whether it will be 2 to the power 3 means we put a bracket here, first we perform this operation 2 to the power 3 and then its power 2. So it simply means 8 to the power 2, or it is first we perform a operation here, so 3 to the power 2, or it is 2 to the, and then result will be raised to the power 2. Okay, so it is 2 to the power 9 or 8 to the power 2. Which one is correct? Obviously this one is correct. This one is correct because our this operation is right associative. We perform this operation from right to left. Okay, so this particular derivation tree corresponds to this. So in this example we want this one and we want to remove this one. So our this operation is right associative. So here we want to keep the right recursion and we wish to remove the left recursion. So simply we will be writing our grammar like E to, we don't want to keep the left recursion. Okay, so by which we can replace E, we will write that here. So we can replace E by A, so we will write A here. So A raised to the power E oblique A. This will be the modified grammar. This will be the modified grammar. Now through this grammar we will be able to generate only the tree of this particular form. Just look here, from E we will start. We are bound to take A arrow E. Okay, so it is A arrow E, and then here is A, so we cannot expand in this direction as we have done here. Okay, so we are bound to expand this one as we have done there. Okay, so E to the power E, and then this E by A, and then this E by A. Now you look at, first this operation will be performed, result will come here, then this operation will be performed. So it is a right associative operation, and this we have achieved by keeping the right recursion and removing the left recursion. We cannot find the tree structure of this form, so so we have removed the ambiguity. Only one tree structure will be generated, which is the correct one. Okay, so if we want left associativity, we will keep the left recursion. If we want right associativity, we will keep the right recursion. Now in this next example, our grammar is almost similar again for the arithmetic expression, but involving more than one operator. So here in this grammar we are having the productions E to E plus E, E asterisk E, A and B. These two are terminals. Okay, so here we two operators plus and asterisk, that is addition and multiplications, are involved. Okay, again this grammar is also ambiguous because in both the productions for plus and asterisk we are having both left and right recursion present. Here also we are having left and right recursion present. Both of these are left associative, so obviously we will keep the left recursion, we will remove the right recursion. But even if we do that, we will be having two different kind of derivations, because suppose if we derive a word W is equal to A plus A asterisk B. Okay, so we can derive it in two manners. We will start from E, we will derive E plus E from it, and because plus has been derived, star we want after the plus, so on this side we are bound to derive A. Okay, now from this E we are bound to derive E asterisk E, and from this E we will derive A because we want A here, and from this E we will derive B because we want B here. Okay, so in this manner we can derive this, and the yield of this is A plus A asterisk B. Okay, now the second method is, from E we will derive E asterisk. Okay, now asterisk we have derived, to the left of asterisk we want a plus, so from this E we are bound to derive E plus E. Okay, now then from this E will derive A, from this E will derive A because we want A plus A, and from this E we will derive simply B, because after the asterisk we want B. So yield of this is also A plus A asterisk B. Okay, so both are the derivation trees for the same word, but both trees are having the different meanings. Here, if we look at what is the meaning of this expression, which operation will be performed first? This asterisk will be performed first, because the result of this asterisk operation will come here and then it will be added here. Okay, so A plus A asterisk B, it will basically represent this expression. Now here, this plus operation will be performed first. First these two A will be added, result will come here, and then this result will be multiplied by the result of this. So here, first these two A will be added and the result will be multiplied by B. So both trees are representing the different expression. Now which expression we want? As per the rule of the arithmetic expressions, we want to give higher precedence to the plus this multiplication operator. Okay, this plus is having the lower priority. Okay, so if this is a precedence problem which we have to solve, precedence we are having A and B, so operands will be evaluated first, then among the operators star will be evaluated first, and then this plus will be evaluated. And among these two operators, both plus and asterisk are having the left associativity. So we have to modify our grammar according to this. So associativity problem we know how to solve. Now we have to look at how we can solve the precedence problem, how we can remove the precedence problem. So this can be removed through the use of levels. The higher is the priority of the precedence, higher is the precedence of the operator, higher should be the level of this. Okay, meaning thereby the least priority operator should be derived from the start symbol, and rest other operators should be derived at further successive levels. So this you have to keep in mind. The lowest priority operator, here we are having this plus as the lowest priority operator. So this plus operator will be derived from the start symbol. So our start symbol is E. So we are start writing our grammar E. So we are going to write the productions of E. So plus will be derived from this E. Okay. So our production will be of this form E2. Now we have to use plus. Okay. Now plus is left associative. So means we want to keep the left recursion. So that's why we'll keep this E here. We'll keep this E here. Now on this side E cannot come because we have to remove the right recursion. Okay, so we will not. Now here what will come? Here the next level will come, because after this we can generate either the pluses or we can generate the asterisks. Okay, pluses we will be generating through the left recursion, and rest anything we will be generating from the next term. Okay, so suppose that next term we are calling as T. So that's why we will be writing something like E plus T. So whatever pluses will come, we will be generating through this E, and whatever else will come, that will be generated through T. Okay. Now it is possible that our expression does not contain plus at all. Okay. So it is containing only the other things. Okay. So how we can go there? Because we will go there only through this plus. So we should have a method of directly going there. So from E we can directly go to T. So if our expression does not have pluses, plus operators, then we can directly go for the other operators or other things which can be generated through this T. Okay. Now the next level of the precedence is asterisk. So through this T, the next level will be generated. So through this T, we will be generating asterisk. Now among the asterisk, this asterisk is also the left associative. So from this production, we have to keep the left associativity. Left recursion. So left recursion, here we are driving this from T. Here we were driving it from E, but here we are driving it from T. So we'll keep a T here. So left recursion we have kept here. Now we don't want to keep the right recursion. So means something else should come here. Suppose the next level things will be generated from this F, this variable capital F. Okay. And suppose asterisk does not appear in the expression, then and we have to go to the next level, then we should have a method to directly go to the next level. So we will be writing F here. Now what is the next level? Next level is simply the operators A and B. So here E was directly deriving A and B, but now A and B will be derived because these are having the highest precedence, so they will be derived from F. So through this F, we will be deriving either A or B. In this manner, we will be writing the grammar. So what we have learned up till now, precedence we will be handling with the help of levels. The lowest precedence operator should be generated from the start symbol, and further the next precedence operator should be generated from the next level variable, and this will go on. This legacy will go on. Okay. So A and B. So now we have defined this grammar and we claim that our this grammar is not ambiguous. So let us try to generate the given word from this particular grammar. Okay. So again we are starting from E. We are starting from E. Here we want plus. Okay, so we have to use E plus T. So we will use E plus T. Now through this E, what we want to generate? We want to generate through this E A plus A. Okay, so plus we have already generated here. So through this E, we will directly go to through this E we want to generate this A because plus has already come here. So E to A we cannot directly go, so we can go from E to T. So we will be writing E to T. There is no other option with us, available with us. Now from T, what we want to derive? We want to derive A. From T, we do not have anything which directly derives A. So we can go for F. From T, we will go for F. From F, we can derive A. From F, we can derive A. So in this manner, we are expanding the leftmost available variable. Now we have to expand this T. This T, from this T, we cannot derive plus because it can only derive a star. Okay. So now we want a star here, so we'll be using T asterisk F. Now from this T, what we want to generate? We want to generate A because a star has come before the star, and after this plus we need an A. T, we cannot derive A directly from T. Okay, so we'll go from T to F and then F to A, like in this manner. Okay, so we have derived A here. Now from this F, what we want? We want to derive B. So F to B we can directly derive. So F to B we will derive. So in this manner, we will derive this expression A plus A asterisk B. And if you look at the structure, it is the required structure. First, this F will be evaluated, its value will become A. Then this T will be evaluated, its value will become F, or in turn A. Okay, so A will come here. This F will be evaluated as B, so B will come here. So A asterisk B, this operation will be performed and its result will come here. And then here F will become A, then T will become A, then E will become A, so A will come here, and A asterisk B has come here, so these will be added. So first this multiplication will be performed and then this plus operation will be performed. So our expression in the required form will be evaluated. And we cannot generate any other tree than this. Okay, so there is no ambiguity, so it is an unambiguous grammar. It will generate the correct tree, it will give the correct sequence of operations. So it is keeping both things in mind, the level of the precedence of the operators and then also the associativity of the operators. Now come on this example. This is also the similar example. Here we are having three operations plus, asterisk, power. These three operations we are having, and this is the grammar. Obviously, this grammar is also ambiguous, and we can take any appropriate word and prove that this grammar is ambiguous. So I am not going into that detail. I am directly writing an unambiguous grammar corresponding to it. Here we are having both left and right recursion. Here also we are having both left and right recursion. So we will first look at the precedence. The highest precedence is the operand. It will be evaluated first, then this power operation will be evaluated, then this asterisk multiplication will be evaluated, and then this plus will be evaluated. If we look at the associativity, this power operation is having the right associativity, and this asterisk and plus operation, these two are having the left associativity. So keeping this information into mind, I am going to write the unambiguous grammar. So I will start from the S. As I have told you that least priority operator should be derived from the start symbol. So least priority operator is plus. So from this I will be deriving plus. Now for plus, what I want the left associativity. So left recursion I will keep. So I will write as here, and then I will generate the next level. So next level, suppose I say it is A. So I am writing A, and then I must have a way to directly reach to the next level. If this plus operation is not present in the expression or when it is not required. Okay. So I have gone to A. Now from A, the next level operator will be generated. The next level operator is asterisk. So I have to generate asterisk, and asterisk is also left associative. So I have to keep the left recursion. So I will write A here, and then I have to generate the next level, that is, I say suppose B, and then I should have a way to directly reach to the next level, that is on B. Okay, so these will be the productions of A, and then for B, next precedence operator will be generated, that is the power operator. So I have to generate the power operator, and in this power operator, associativity is right associativity. So I want to keep the right recursion. Right recursion means if B is here, so B I should write here. Here should come the next level. Suppose that is C. Okay, and then I should have a way to directly reach to the next level, that is C. Now through this C, the next level will be generated, that is the operand itself. So through this C, I will be deriving. So this will be the simple modified unambiguous grammar corresponding to given this ambiguous grammar. So this was all about the removal of the ambiguity which I wanted to discuss. There may be some other kind of ambiguities also present, but whatsoever I have discussed, that are the most common kind of ambiguities. Okay, so this was all I wanted to discuss. Thank you.